All right, today we're diving into a research paper that proposes a completely new way of looking at the universe. We're going on a bit of a journey here into computation, physics, and even philosophy that might just change how you think about, well, everything. And we're going to start with a huge question, one that scientists and philosophers have been wrestling with forever. Is time actually real? Is it a fundamental part of the universe, or is it just an illusion? This isn't just some late-night thought experiment. It's the central mystery we're going to try and solve today. And the key to that whole mystery is right here, in this pretty radical idea from the source material. It says that time isn't a dimension we travel through. Nope. Instead, it's what's called an emergent property, basically a side effect of changes that are happening in space, designed to make sure causality, the law of cause and effect, is never broken. So let's break down how we get to that wild conclusion. Okay, so before we can really get our heads around this new idea, we've got to look at the tools we're already using to describe the world, and more importantly, where they fall short. Because describing reality, as you can imagine, is really, really hard.
A classic tool for this kind of thing is the cellular automaton. You can think of it like a video game world, like Conway's Game of Life. It's a grid, and the future of each little cell is decided by its neighbors. They're awesome for modeling stuff like wildfires or how populations grow, but they have a major weakness. They're usually stuck on these rigid grids and really struggle when you need to handle multiple, overlapping layers of information at once.
Okay, another huge one is the tensor. Now, I know that word can sound super intimidating, but stick with me. The basic idea is actually pretty simple. A tensor is just a really powerful way to organize different kinds of information across different dimensions. It's really just a way to level up concepts we already know. So, let's just build it up step by step. A rank 0 tensor, that's just a scalar, a single number, like the temperature outside. Simple, right? A rank 1 tensor is a vector, which is just a list of numbers that has a direction, like velocity. A rank 2 tensor is a matrix, a grid of numbers. And you can just keep stacking them up to represent more and more complex things about the world. And yeah, this visual here really helps lock it in. Think of tensors like nested folders on your computer. A single number is a scalar. Put a bunch of those in a list, you get a vector. Arrange those vectors in a grid, you get a matrix. You just keep nesting them. It's a really neat system for organizing complexity. But as we're about to see, this complexity can cause some pretty big headaches. But, and this is a big but, here's the problem. In the traditional math, this whole system has some weird gaps. Like, what exactly is a tensor with 0 dimensions, or a rank 0 tensor in 0 dimensions? These situations can actually lead to mathematically undefined results. They create these fuzzy spots in our models that make things way more complicated than they need to be, especially in fields like advanced physics. So, clearly, we need a better system. And that is exactly where this paper comes in with its big solution, a new framework called the Multi-Dimensional Cellular Automaton, or n-CAk for short. And what's so cool about this is that the core idea is actually super simple. It says, hey, instead of getting lost in these weird abstract dimensions, just think of reality as a stack of information layers. Each layer represents something different about a system, but they all exist in the same place. It's a much more intuitive way to think about complex data. Let's use the paper's own example to make this real, simulating a wildfire. To do that, you need a bunch of different kinds of information, right? So you just create layers. Layer 1 is a map of the ground's elevation. Layer 2 maps out what kind of plants are there. A third layer tracks the wind. And the final layer, well, that's the fire itself. All these information layers are just stacked on top of each other. And with that example, that crazy formal name suddenly makes a lot more sense. M is just the total number of layers you have, so 4 in our wildfire example. N is how many dimensions each layer has, like a 2D map. And K is the number of active layers, the ones that are actually allowed to change. In our fire simulation, the fire layer is active, while the elevation map just sits there in the background. So this whole layers idea, it's not just easier to think about, it's actually way more solid mathematically. It totally cleans up those fuzzy spots we were talking about with traditional tensors. It just makes sure nothing is left undefined. And you can see it right here. On one side, you've got the old way with all these weird, undefined holes where the math just breaks. But on the other, with this new framework, every single combination of layers, dimensions, and active states has a clear, logical meaning. There are no more gaps. So let's look at the details here. A traditional tensor with 0 dimensions used to be undefined. Now, it's just a function that works on a single value. Makes total sense. A situation with 0 active layers. That's just a static picture of information, like a map. And that really tricky 0 to the power of 0 problem, it just becomes a simple set of numbers. See, it's so clean. Okay, so we've got this awesome new tool for describing complex systems, and it doesn't have any mathematical holes. That's cool. But what does any of this have to do with time? Well, this is where it all comes together in a really beautiful way. Because the biggest, most mind-bending takeaway from all of this is that in this new model, time is not a fundamental dimension of reality. It's not the fourth dimension we always hear about. It's something else entirely. So think about it. In this new view, there's only one thing that's really there: space. And I don't mean empty space. I mean the complete collection of all those information layers: the elevation, the wind, the fire, everything, all existing together in one giant, complex data structure. And the only other thing that exists are the rules, the physics, the laws that say how that space is allowed to change from one moment to the next. And the most important rule of all is that causality has to be preserved. Cause has to come before effect, always. So where's time in all this? Well, time is just the name we give to that process of change. It's not a thing itself, it's just the measurement of the modifications happening in space. It's the bookkeeping we do to make sure the rules of cause and effect are never ever broken. It emerges from everything else. And this quote from the paper just nails it. The smooth, continuous flow of time that we all feel could just be our brain's way of simplifying an unbelievably huge number of tiny, discrete, computational steps happening at the most fundamental level of reality. Okay, so why does any of this matter? I mean, this is pretty abstract stuff, right? Well, it's not just a mathematical game. This new way of looking at things has some huge, real-world implications. I mean, what does this new framework really unlock for us? Well, for starters, it gives us a much more intuitive way to think about really complex physics by just thinking about layers of information. It's also a seriously powerful new tool for running simulations, whether that's for AI or for modeling climate change. It might even help us simplify some of the gnarliest equations in physics, like in general relativity. And of course, it just gives us a whole new way to think about, well, reality itself. And that's what I want to leave you with. If something we feel so directly, so fundamentally, like time, can just be an emergent property of space and its rules, then what else about our reality is just a simplification, an illusion that comes from a computational process that's more complex than we can even begin to imagine?